Thank you very much for the introduction, Ray, and thanks for having me here today to give this primer on fairness in clinical settings. So machine learning models are starting to catch up to human performance in many real-world clinical tasks, including radiology. And as a result, they're soon to be integrated more and more into real-world clinical care. So here's a graph showing the number of FDA-approved AI-enabled medical devices as a function of the year. And you can see that as we approach the deep learning era, the number of approved devices is skyrocketing. And today, there's over 500 approved devices, with over 3/4 coming from radiology. Here's one such device from a company called Enemies AI, which provides the software to do diagnosis of pneumothorax from chest X-ray. And this software is also being used in Australia and the UK, among a few other countries. And so machine learning models are very good at minimizing overall training error. But if you care about something other than performance, maybe you care about fairness or performance of some subgroups, ML models have been shown to have failure modes in that thing. So as an example, here's an article from Stat News last week, which shows that tools to predict stroke risk work less well for Black patients. If you dig into the paper where the study comes from, you find that there's this table which shows a few different stroke risk prediction models, and they stratify by race and sex. Here they show the C index, which is the same as URLC. If you look, for example, at these machine learning models, we find that these models perform much better, for example, in white women compared to Black men. Okay. And with the advent of recent large language models such as ChatGPT and GPT-3, perhaps there's also eventually going to be a use for such models in a clinical setting, for example, to help write clinical notes. So here's a paper that I was part of in 2020, where we looked at essentially using large language models for sentence completion. So here we have a template sentence. For example, race, patient, became belligerent and violent, sent to go in the blanks. So we asked this large language model called Cybert to go in the blanks, and we find that depending on what the race is, the patient is sent either to the hospital or to prison. So clearly, this is not a desirable autocomplete from the model. In the paper, we also looked at biases in terms of downstream performance between different groups, and we find, for example, that there are significant gaps in the recall, often favoring larger majority groups. So what's the point of all this previous work? Well, the point is that there is all these notions of fairness that are out there. Perhaps we would like to formalize fairness in some way. What does it mean for a model to be fair? We mathematically define what that fairness means. So that's what the field of algorithmic fairness is trying to show. Okay. So to define what algorithmic fairness is, perhaps easy definition is it's fairness arising from properties of this model, either its predictions, its behavior, some behavior of this ML model. But inherent in that explanation is also what is this algorithmic fairness not? And so there's many things outside of this pipeline for which algorithmic fairness does not cover. For example, how the model is used downstream. Right. So the ML model outputs some prediction as part of some clinical decision-making system. And if the physician selectively chooses to trust the system for different patients or for different groups, that can be a source of bias, certainly. And if these decisions eventually lead to downstream treatment and diagnosis, depending on how the treatment can interact with different populations, that could be another source of bias. There's also upstream sources of bias as well. For example, generally in an algorithmic fairness analysis, we assume that the data that we observe is going to be what the data is deployed on downstream. But this may not always be the case. For example, you might have selection bias, in which you have certain subgroups that are more represented in the population than in your data set, and vice versa. For example, due to inequality in access to healthcare, you might have certain types of distribution shift, right? Where the distributions you see during deployment is not exactly what you see during training, and there's no guarantees on what fairness performance you will observe in that new distribution. Though this is an area of recent work. And so this is really a caveat to say we're mainly caring about what happens in this black box, but there's many other things going on that we do not necessarily observe or account for in our evaluation. And the main reason is because accounting for these other considerations would require either a lot of assumptions, which may be too strict or unrealistic, or user studies, which are very expensive and time-consuming. So to give the caveat, which is that a model that is fair, according to the definitions that we will see, doesn't necessarily mean that's socially equitable or has maximum welfare or something like that. It's just simply the ML model has some behavior that we like to have. Okay. So that's the algorithmic side of algorithmic fairness. What about the fairness side? Well, there is no unifying definition of what it means for a model to be fair. There's many definitions out there, maybe tens or hundreds of definitions. So here's a few of them just to fill up the screen. We have group fairness, which we'll talk a lot more about today, which is widely used in the healthcare setting. Then there's, for example, Minimax fairness, subgroup fairness. There's fairness definitions that do not even use the group as an input. And then you have all these causal definitions of fairness that are based off of some causal graph, which you either assume or you find. And then these are based off of paths in the causal graph. And so today we will focus on these two definitions: group fairness, which is the most commonly used definition, and the minimax spatial fairness, which we'll mostly have as an alternative to group fairness. And then the other definitions, there's many of them. Just keep in mind as we go through that these are not the only definitions that exist in different things. Here's a roadmap for the rest of the talk. We'll start by defining what group fairness means, and then we will define minimax spatial fairness. And throughout, I'll show examples of these fairness definitions being used in the chest X-ray diagnosis setting, which is where I'm most familiar with. But such findings that we conclude will also be applicable to a whole bunch of other medical settings as well as other real-world machine learning tasks. Then we go back and look at disparity in data. So here we'll look at one upstream source of disparity called label bias and how that may impact our analyses and our fairness metrics. Then we will switch gears shortly to talk about shortcut learning. Okay, and so this is essentially the one sentence summary is that shortcut learning happens when the model takes advantage of dispersed correlation in which we do not want it to take advantage of, leading to disparate performance in TPR and FPR in some downstream task. And then we'll connect shortcut learning back to group fairness. Finally, I have some concluding remarks in terms of practical suggestions for how to deploy your and how to do your fairness evaluation in your particular machine learning task. Okay, so that's it with that. Let's start with what is group fairness. So for this slide, I'm gonna keep everything very general, and then we'll specify it down to our problem setting in the next slide. So here we have some labels, predictions, and group as random variables. And here the label could be a binary classification task, it could be a regression task, could even be a string of text or an image or something. But there's three main fairness concepts that are used in the literature, and these are based off of prior work in economics and philosophy. They're independence, separation, and sufficiency. So for example, independence says that our prediction y hat should be independent of the group. Okay, and so all these fairness principles are defined as these conditional independence statements that apply to these three random variables. Let's be a bit more specific. Let's look at only the binary classification setting, and specifically the setting where our prediction is a binary variable as well. We'll relax this in a couple of slides, but for now we assume that we have a binary prediction. And let's specialize these definitions to our use case. Okay, so for example, independence we saw was y hat independent of G. In the binary classification case, this is called demographic parity. And if you think about what this independence means, it's really saying that the two groups have the same predicted prevalence. Okay, you can work through this exercise for the rest of the definitions, and you find, for example, with separation, this implies equal FPR and FNR, also called equalized odds. And then because this definition is maybe too strict, it requires two things to be equalized at once. We can also define a separate definition called equal opportunity, which allows us to only equalize one and one. You get to choose which definition you want to equalize. And similarly, there's sufficiency, which can adapt to the same setting, which calls for equal precision and negative predicted value. Okay, so essentially in the group fairness setting, in the binary classification setting, these definitions correspond to simply equalizing some trivial prediction error rate or some prediction metric of our model. Okay. Now the first question is, which of these definitions should we choose? There's many of them, there's 6 of them here. Which one should we choose? Can we choose all of them at once? Which one is the best for your setting? Well, it turns out that you cannot choose all of them at once. So this is a theorem called the impossibility theorem, and there's many of them out there. Here's an informal statement, which says that given that your base prevalences are different between groups, for example, that men and women have different rates in the outcome, and that your classifier is not perfect, that you have less than 100% accuracy, you cannot achieve simultaneously more than one of these three at once. So you cannot achieve equal, FPR, FNR, and predicted prevalence. As a corollary, specifically, you cannot achieve equal precision, specificity, and recall. So essentially, there's all these trade-offs that happen between these metrics in the real world, and then we have to decide which metrics we want to optimize and which ones we want to pick. Okay, So the first question is, are existing chest history classifiers group fair? So this is a paper that we had a couple of years ago in Nature Medicine trying to answer this question. Okay, so here's a general setup of our experiments. We start with some data sets, some overall population, and then we have these X-ray images. We'll talk more about what these images are and what they look like in a second. But the idea is that we take these images and we train a deep neural network, CNN, to predict some task called no finding. No finding is a particular task where a no finding of 1 means there's absence of any pathology. So no finding of 1 means the patient has no disease, any of the diseases that we know of. And no finding of 0 means the patient has some disease. So this is simply a disease predictor. Does the patient have a disease or do they not? Okay. And then in particular, we look at the false positive rate. So this corresponds to equal opportunity if you think about the definitions. And the false positive here, if you think about it, is when we predict someone to have no finding, will they actually have a finding, which is very detrimental because they might be withholding treatment from that particular group, right? And so here, the pipeline is we train this model, then we examine the FPR, the false positive rate of each of the groups to see if there's any disparities. So the question is, are X-ray classifiers group fair with respect to this particular definition? And well, first, let's look at the data set for a second. And so what these data sets look like are there are images from a particular study. So one patient can have multiple studies, and one study can have multiple images. So here you have a frontal image and the lateral image. Generally, we treat these images as independent. So we do not care about the patients that they come from. We treat them as independent samples with some label. And we'll talk more in a second about how you actually get these labels and where they derive from. But for now, let's assume that these are correct labels. Okay. Then we simply train our model to predict these labels, in particular this no finding label from the images. And in terms of data sets, we have many data sets, many really large Texas data sets. So here we have 3 that are shown from Boston, Stanford, and Bethesda, so from across the US. The number of images here order hundreds of thousands, and they have varying demographic makeup as well within each group. So for the purposes of this talk, I will show results only for Minimax CXR, but the results from the other data sets are shown in the relevant papers that are cited. Okay, coming back to the question, are Texas classifiers group fair? Well, in this paper, we looked at the FPR, false positive rate of each of the groups, and we find that, for example, females have higher diagnosis along with younger populations, Black and Hispanic patients, as well as those that are Medicaid insurance. It's indicated by the higher false positive rate. And if you specify down to a particular intersectional subgroup, for example, Black women, you often see even higher disparities. Okay, so this is a pretty simple result that shows that there are indeed gaps in false positive rate between different groups when you train a model to predict no finding. And perhaps this isn't very too surprising or too interesting, but it's apparently worthy of an Nature Medicine paper. And so the question is, can we go deeper? Can we dig deeper into those results and come up with the better finding? And so there's one thing that you need to know or to realize in order to dig deeper, which is that ML models don't output a binary prediction, they output a risk score. Okay, they output a number between 0 and 1. And then to compute the binary prediction, we threshold that value at some threshold. Say, nominally 0.5, but you can choose a different threshold. And the point is that the setting of the threshold is very case specific. It's very dependent on the deployment setting, on the physician's preference, and so on and so forth. So it's very hard to know exactly what the threshold will be beforehand. And there's many ways to compute what the threshold should be. Here's one such method, which is if we assume that false negatives are some C times as costly as the false positives, and we're trying to minimize this cost function, it turns out that this implies that you have a fixed threshold for other groups, which is a function, a very simple function of C. Okay, and then any other thresholding rule incurs a higher cost. So this is sort of a cost-based way to derive your optimal threshold. So there's other ways to do it as well, based off of constrained optimization, things like that. But the overall summary is that the overall threshold that we want to choose is highly dependent on the deployment setting, on the physician preferences, and so on and so forth. So it's impossible to know beforehand when training a model what the threshold may be. Okay, and so the real question is, we define fairness based off of prediction at a fixed threshold, based on the binary prediction. But can we define fairness now based on the risk score? Can we either think of fairness in terms of all possible thresholds that we have, or just some fairness definitions based on the original risk score? Okay, and so to do that, we need to have a couple more concepts. The first is this concept of calibration. Okay, so plainly put, a model is calibrated if the probability that you have a positive prediction, given that you have some predicted probability, is equal to that probability. So in summary, basically, if your model predicts, for example, that you have a 35% positive probability of no finding, roughly 35% of those samples should actually have no finding. Okay. This really just says your prediction probability means something. It's meaningful in the real world. And one thing you notice that differences in per group calibration is also a disparity versus disparity. For example, here's a synthetic example where we have what's called a calibration curve, which maps your prediction fraction of positive predictions as a function of their probability. And we find that, for example, if we were to threshold patients at 0.5, group 2 here is very poorly calibrated, right? Because it overestimates risk or underestimates risk. And so we see that if we threshold it at 0.5, we're actually having a true risk threshold of 50% for group 1, but true risk threshold for group 2 is now like 75%. So we're only treating patients in group 2 when their true risk exceeds 75%. So this is clearly a major source of disparity that we want to correct. And we'll get to that in a second. And to summarize this graph into one metric, you can use something called the expected calibration error, which is essentially this area between the optimal calibrated model and your calibration curve weighted by the samples that are in that within each bucket. And here, the calibration error for 3.2 is about 0.17. It's normally between 0 and 0.5. Any questions so far? Okay, so now that we're in risk score land, we can do some fancier things. So first, we can plot the histogram of prediction probabilities for each class of our data set, and then for each group as well. So this is back to the diagnosis model, and we see that if we use, for example, 0.3 as the threshold, we can compute a true positive rate and a false positive rate for that threshold, basically by integrating over this area in the graph. So for example, this area in the graph for y equals 0 corresponds to the false positive rate, and this area in the graph corresponds to the true positive rate. This thing, we can plot this as one dot in your AU ROC curve, or your ROC curve like this. And then by sweeping over all the thresholds, we can get a curve over PPR and FPR, explain trade-offs between those two metrics as we change the threshold. Okay. So let's go back to this Diagnoses paper. And if we plot the ROC curve for black and white patients, they look like this. Okay. And surprisingly, the ROC curve is almost identical. The area under the ROC curve is about the same between the groups. But if we threshold at a constant threshold, we do see that there's this gap in the FPR. So here we choose the threshold based on F1 maximization. So we're getting a threshold of 35% for all the groups. And we see that here's the 10% gap in the diagnosis that we saw in the markup. Right. But what if we do a very simple strategy, which is we know that every single dot on this point corresponds to on this curve corresponds to a threshold for each group. What if we were to pick thresholds in a way such that the points coincide? In that way, there is no more FPR gaps between the two. So we can do exactly that in this per group thresholding method. So here I've just chosen a bunch of random thresholds in a way such that the dots are not on top of each other. And if you look at the TPR and FNR performances, here the gap is almost 0. Right? We have 0 FNR gap, 0 FPR gap. So this satisfies equalized odds. And compared to the previous model, we do see that we've improved the fairness of this model significantly by using per group thresholding. Okay, and here you can see the ROC between the groups are very similar. And similarly, the calibration is quite good between all the groups. So, okay, are we done here? Can we just deploy this model at different thresholds? Is this a good model to use? Well, probably not quite, because there's many issues that we have with per group thresholding. So for one, if you remember from the previous couple of slides, this sort of implies that you have different FP and FN costs for the groups, which is again another source of disparity. We're assuming, for example, that some groups have higher costs, false negatives than others, which may or may not be desirable. Secondly, we have to know the group identity, right? We have to know what group the patient is when they come in order to know which threshold to use. And for example, in Mimic, in the ICU setting, many patients come in and we do not know what their race is because they either do not want to identify with the race or they're unconscious and they're unable to provide a demographic. And so for those patients, you're going to have wildly inaccurate results. And finally, in the case where the ROC curves do not overlap, then you have to basically worsen the performance for one group systematically, which again has some ethical issues. So I think per group thresholding is a very easy way to achieve equalized odds, but there's all these caveats with it that makes it perhaps not very good to use. So now we're ready, I think, to tackle fairness for risk scores. Okay, so we talked about the case where y hat is in the set 0 and 1, but now what if it's in interval 0 and 1? So now it's a predicted probability. Okay, so to defend group fairness, we can use the same metrics, the same criteria that we saw before in terms of separation and sufficiency. So here, separation, remember, is this independent statement. And what this really says, if you think about it, is that if you look at this y equals 1 predicted probability graph, that these two curves should be identical, right? That these two histograms should be the same between the groups. That's what this statement says. The issue is that this is a very strict statement that requires two distributions to be the same, which is very hard to satisfy in machine learning. And so there's a relaxed version of this called probabilistic equalized odds, which simply says, instead of having the whole distribution be the same between the groups, we now just want the mean to be the same between the groups. For example, the mean of one group might be here, and the mean of another group might be here. We just want to merge them so the means of the two groups are the same in terms of the predicted probability. So again, this means that the average prediction for a certain group of y equals 0 should be the same as the average predicted probability for that group, for a different group of y equals 0. Okay. And so that's what separation corresponds to in the risk score thing, probabilistic equalized odds. What about the efficiency? So if you think about this statement for a bit, you realize that this actually implies that the two groups have equal calibration curve. Okay. And that's why we talked about calibration earlier. The two groups has equal calibration curve is our desired property for sufficiency of a risk score. Now, the thing is, equal calibration curve may or may not be good because the calibration curves could both be very bad, right? The EC could be very high for both groups, and you will still satisfy this property. Now, it turns out that we can go from essentially having equal calibration curve to having perfect calibration curve for both groups using some post-hoc calibration methods such as plot scaling or synchronic regression. So the idea is that there's some function G which maps between probabilities, which allows us to go from equal calibration curves to per group calibration. And this is desirable property because now both groups are calibrated perfectly, which allows us to have risk thresholds that are calibrated with respect to actual risk. Okay, and to evaluate either of these metrics, we can look at the expected calibration curve that we saw. Any questions so far? Okay, so similarly, there's also impossibility theorem that we have for the risk score thing. And this one's a bit more intricate. Essentially, it says we have these three properties here. We have property A, which is that the groups have perfect calibration, aka sufficiency. We have that the two groups have equal expected distribution in terms of scores, which is separation. It turns out that it's impossible to satisfy all three of these at once unless your predictor is perfect or they have equal base rates. Okay, so my take on this is that there's inherent trade-offs between equalized odds and per group calibration. Both of these are desirable, but it's not possible to achieve both of them at the same time. And it turns out from other work, we see that unconstrained classifiers tend to prefer calibration. Okay, so unconstrained classifiers, ERM classifiers, tend to prefer calibration over fairness. And we'll see example of that in a second. So the takeaway here is that there's all these trade-offs between different metrics. You have to pick and choose which metrics you want to equalize or satisfy. Okay, so let's look at some more experiments. But first, how can we enforce equalized odds? Well, here's a very simple way to do it, which is we have our ERM objective, which is to minimize loss over our training set. And then we add in some regularizer, lambda temp. Okay, so we just add in this extra term to our loss function. And what is M? Well, if we care about equalized odds, we just want to equalize the two distribution, right? The distribution between the y hat for group 1 and group 0. And so here's one such regularizer you could use, which essentially sums over all the possible y's. There are two y's, and then all their groups, and then regularizes the distance, some distance metric between your distribution of y hat for that particular group and the margin. Okay, for this distance function, you could use something like MMD. You could use just the mean between the two metrics, which corresponds to the probabilistic equalized odds, or you could use an adversary, which predicts what the group value is given some criteria. And so all of these methods correspond to other methods that people propose in the literature, but let's apply them to our X-ray setting for no finding diagnosis problem and see what that gives. So we're going to vary this lambda value and evaluate all the metrics that we just saw, see what happens as we increase lambda. Okay, so lambda equals 0 corresponds to E or M. And if we have high lambda, that corresponds to high fairness. So, okay, first thing we see is that as we increase lambda, and here we have performance for each of the groups, as we increase lambda, we do see that all of the fairness metrics come together. So recall and this value of probabilistic equalized odds essentially eventually equalize to some point estimate. So we do achieve fairness with high values of lambda. The issue, first of all, is that we have worse calibration error. So all the groups become uncalibrated, and this again comes from the theory that we just saw, the impossibility theorem. Calibration error goes up when you increase fairness. The perhaps more problematic, though, is if you look at the EROC of each of the groups, we find that group fairness worsens performance for all the groups. So as we increase lambda, the EROC for all the groups monotonically decrease. We never increase performance for any group if we enforce fairness. Okay, so this is very problematic, and maybe this is surprising, but turns out that this isn't just true in technical classification. We also find similar findings in clinical tabular data, general ML. So this idea that group fairness worsens performance for our groups has been demonstrated as well in machine learning. So let's summarize what's good and what's bad about group fairness. So the title of this talk was group fairness, hurtful or harmful. And I think based on the findings here, we can probably conclude that group fairness is not helpful. So here's the case against group fairness. First, we see that in the binary classification case, where the prediction is a binary value, there's all these impossibility theorems, and we can easily achieve it through per-group thresholding, although this gives us, although there's a bunch of issues here. For example, how do you choose the threshold? In the risk score case, we have this possibility theorem between the per-group calibration and probabilistic equalized odds, both of which are desirable, but cannot be achieved simultaneously. And finally, overall, we see that trying to achieve fairness results in miscalibration that is higher ECE and worse performance for all the group. So this is the case against group fairness, and perhaps why it's not necessarily a great metric to use in the clinical setting. So what's a better metric to use? Well, let's get to chapter 2, which is min-max critical fairness. Okay, so this is the recently proposed metric or definition of fairness in the ML literature, which says the following. We have some set of models, right? So here, each dot is a particular model. We evaluate its loss on group 1 and its loss in group 2. Okay, and so you could train these models by varying things like the training set, the hyperparameters, the seed, and so on and so forth to get this grid. Now we define this idea of Pareto optimality. So we say a model is Pareto optimal if you cannot increase the performance of one group without decreasing the performance of another. Okay, so if you think about it, the green dots here are the sets of Pareto optimal models. These are the models where you cannot increase the performance for a group without decreasing performance for another. Right, so these are sort of models that are at the bound of the Pareto curve. Then, what we can do is we can select the model within the Pareto optimal set that has the maximum worst group performance or the minimum worst group loss. So that corresponds to this model right here. Okay, so this is what the Minimax Pareto fairness is. We want a Minimax, we want a Pareto optimal model that's min-max fair. Okay, so immediately we see that there's a few issues with this definition. The first is that this is kind of a relative inference because we don't know exactly what the Minimax model is going to be. We do not know exactly what the best case loss is going to be for a particular group. And so we can only really compare models based on this definition, but you can't sort of definitively say, given a single model, whether it's fair or not for this definition. We do see that we can convert a Pareto optimal model to a group fair model just by simply randomizing the model, essentially perturbing the output in a way where we add in some random distributed predictions to decrease loss for a particular group. So here, if we just worsen performance on group 2, we get a fair model. So of course, this is not ethically perhaps proper because we are just worsening performance for a group arbitrarily. And finally, in like group fairness, which we saw can be achieved with simple thresholding, this requires some reweighting and retraining. So the achieving of this fairness metric is a bit more complex. Any questions about the technical? Any question on Zoom? Is that racially biased for stroke predictions statistically supported? I'm not sure what you mean by that. So in the paper, they do look at their data set for a variety of different scores with CI. So in there's a significant gap between performance of the groups in terms of the test that they use. So I think in terms of significance is significantly different between them. Okay. So then the question is, let's try to achieve this definition of fairness using existing method. Okay. What happens when we try to do so? I will skip over. So I'll talk about this slide. So there's all these different methods which we use to achieve Minimax fairness, some of which do reweighting and some of which are group fairness methods. Okay, this plot shows on the no finding task for Minimax CXR, the performance on each of the attributes relative to ERM. So here, a performance of 0 is the performance of our ERM model. Okay, and the summary here is that no method outperforms simple data balancing. So in terms of the worst group performance, no method outperforms simply balancing the data by your group, and most models do not outperform simply just using ERM. And this isn't a one-off finding from our work. There's some follow-up work from a different group which shows something very similar, where they look at again, no method outperforms ERM in terms of the ranking confidence intervals, though some models do come close, like this optimization-based method. So I think the summary here is that this definition inference that we have, minimax per difference, is desirable. It's nice, but existing methods don't really do any better on the ERM for the most part. So I think this is an area of active research to try to get models which work well in real world data for minimax per difference. Okay, and so now let's talk about sources of security within the data. So we've done this nice analysis in terms of what's within that black box in the original figure, what's our algorithmic fairness properties of our model. But now we want to talk about what comes into our model, the data, right? Specifically, we'll talk about one type of bias within the data called label bias. Label bias here is defined as when we have labels that differ from the ground truth at different rates for different groups. So you can think about some mechanism which corrupts the label for different groups differently. Different groups have different label noise. Okay. So the first question is there any mislabeling at all? Because if there's no mislabeling, there's no label bias, right? And the answer is definitely there's a ton of mislabeling in text S-rays. So how does the labels get derived from text S-rays? Well, we have the images from our study, then the radiologist writes a note, right? So here's what a radiologist note might look like. And then there's an NLP-based labeler, which uses rules, text rules for the text per labeler, which derives our labels. There's about 15 labels. And here we use our labels for prediction. There are sort of two steps in the pipeline in which label bias and mislabeling can come in. So for the radiologist side, prior work has shown that if you compare the performance of radiologists looking at the images, the performance of radiologists looking at the notes, you get a very, very poor disagreement. So the notes actually leave a lot of information out from the images already. Second, if you look at the text per labeler in terms of how accurately it can pull labels from the notes alone, again, the performance is very poor, it's around 50%. And so if you couple these two together, essentially you get labels that are very noisy and very mislabeled. But this doesn't really answer the question, is there any label bias, right? Are different labels biased, or the label noise is different for different groups? And so in our paper, we tackle this question. This is one of the questions we tackle, where we got a radiologist to manually label about 1,200 images from Minimax CXR for us. So these are images labeled as no finding by the text per labeler, and then we manually label these with the radiologist. What's shown here is the performance of the text per labeler, the agreement essentially between the text per labeler and our radiologist for each of the groups. So we do see that overall, the labels are very poor. So about 65% is the average metric here. This corresponds to essentially precision of the labeler. Okay. And so we don't see a degree of label bias between sex and ethnicity. So if we look at age, there's a huge degree of label bias within age. Specifically, labels for older populations are much more corrupt. Okay, the label quality in older populations are much poorer than younger populations. And we think this is because older populations have more complex notes, there's more comorbidities, and so the text per labeler cannot pick up on the signals that it needs to derive the labels as easily as they can for the younger population. Okay, so essentially, this is one potential mechanism for why we observe poor performance in older populations in our model. But what are the implications of label bias? So again, because we have lower quality training data, we have more noisy labels for some of the groups, that can lead to a poorer model. But even when your model is perfect, evaluating on data set with label bias will give incorrect test set metrics, right? Even with a perfect model, if the Ys are mislabeled for a test set, you again get improper test set metrics. So again, all the evaluations that we saw in the last half an hour was for this mislabeled label bias test set. And so can we really trust those metrics at all? And given the fact that we have different levels of label noise, this can lead to higher base errors for certain groups, which again, when we try to equalize performance between groups, certainly will lead to worse performance for the better performing group with no improvement in performance at all for the worst performing. And finally, how do we correct label bias? Well, we don't need more data, right? Because more data from same distribution will do the same thing. We've got a ton of data, or we've got hundreds of thousands of samples. So what we really need is better quality data. We need to sort of correct our data collection process so that we have, less noise in our labels. We have fairness of our data collection. Okay. One way to do that, for example, is to use a better quality labeler. There's some research in that direction. Okay. So I'll quickly talk about, switch gears and talk about shortcut learning, which is a recent phenomenon in for machine learning models, and we'll relate this back as another source of potential disparity that explains our gaps in FPR and TPR, which we saw in the histogram. Okay, so ER models, again, are very good at minimizing overall training loss, but they're very bad in terms of learning spurious correlation. So here's a figure from this paper that trains a bunch of convolutional networks on ImageNet. And let's look at the examples for which the convolutional network makes an error. And these are the top predicted probabilities for each of the images that we see here. So it's clearly, we see that the classifier has linked the skin color of the person in the image with the sport that they're playing. Okay, so if you're darker skinned, you play basketball. If you're Asian, you play ping pong, and so on and so forth. And it turns out that this rule based on skin color probably performs really well in the ImageNet because there is that correlation within the data set. But again, you perform really poorly for Asians who play soccer, right? So we would ultimately like to remove these spurious correlations from our data set in order to get more robust models. Okay, so how does this setup work exactly? Let's go with a very simple toy example, which is this idea of classifying cows versus camels. Okay, so we have essentially these images of cows and camels, which can either be on desert or grass. We're going to change our nomenclature slightly to refer to the background as the attribute. So an attribute here is males, females, desert background, grass background. Our label here is we're trying to predict, which is cows or camels. And then we define a group as attribute class labels. Okay, so here cows on sand and camels on grass, and so on and so forth. The idea is that in your data set, most of the camels are on sand and most of the cows are on grass. We've got many samples from these two categories, very few samples from these categories. So really the question is, if you train an ERM classifier to predict cows and camels from this data set, what would happen? Well, likely you would probably learn this classifier, which is that your prediction is a cow if the background is grass, otherwise the prediction is camel. Right, but let's try to dig a bit deeper into how this classifier might arise. So let's define what's called the spurious strength, which is the ability first to predict the attribute from the image, and then the ability to predict animal from the background. So the ability that our image encodes the attribute, and then the ability of us being able to predict the label from the attribute. And then the variance rate is simply how clearly can we predict the image from the animal on its own. And informally, we say that we have shortcut learning when the spurious strength is higher than the variance rate. So when we using the background the classifier, then we use the animal itself. So crucially, we have two ingredients for shortcut learning. The first ingredient is again that we can predict the attribute from the image. The second ingredient is that the attribute is correlated with the label itself. And we'll come back to this test in a second. Okay. So what we get if we use that ERM classifier is that we get very, very low accuracy on these minority groups. The cows that are on sand and the camels on grass, right? To connect this back to what we saw before in terms of fairness, we can essentially receive these accuracies as TPRs and TNRs, and we can define this metric called the worst group accuracy, which is essentially the minimum across these four metrics. Our goal in shortcut learning, aka supplementation shift, is to maximize the worst group accuracy. Okay, and you can show that if you try to maximize worst group accuracy, the classifier that results is one that does not make use of the shortcut. We're trying to maximize performance on the camels and grass, cows and lizard. Now let's connect this back to the group variance setting. We're trying to minimize the distance or the difference between TPR here and TPR here. So we do see that the two objectives in terms of maximizing all of the errors versus minimizing distance between these two errors are aligned, but they're not exactly the same criteria. Okay. And so we do see though that shortcut learning is one mechanism to cause these gaps in TPR and TNR. So here we get TPR desert high and TPR grass low. Okay, and even more importantly, if you try to use this ERM classifier on a different attribute, for example, cows on snow, camels on snow, you can get very poor performance. Okay, so we've got a bunch of theory covered, or at least a toy example. Does this happen in the real world? is there shortcut learning in real-world medical imaging prediction? And the answer is absolutely there is. So at the beginning of the pandemic, people in the field were very eager to use these deep learning models to predict COVID-19 from chest X-rays. Okay, and so the good news is you have these really large data sets containing people with no COVID-19 from before 2019. You have hundreds of thousands of images, which we saw patients with no COVID. The issue is, though, is there's very few samples of people with COVID, and most of them come from different sites to where your no COVID patients are in. So we do see that there's data sets with 100% COVID and data sets with no COVID. So there's a correlation between the attribute, which is the site where the images originate, and then the label itself, which is COVID or not. And we can predict the site of the image quite easily using a neural network. So the images from different sites look very different, and so we can predict the site from the images very easily. So if you remember, these are the two ingredients that we have for shortcut learning. So what happens when we try to evaluate our model with a shortcut? We find that we get really good performance if we evaluate it on the training set, essentially the same distribution of the training set. But if we try to evaluate it on an external data set, we get much worse drop in ERLC. Okay, so the question is, does this happen in chest X-rays? In no finding diagnosis, can race be a shortcut? So the two ingredients that we saw first are, can we predict race from X-rays? Well, this is the main subject of Judy's talk, so I won't talk about it anymore. The second ingredient is race correlated with the label? And the answer is yes. So we do see different rates of the outcome if you're no finding for different ethnicities and sexes and groups. And could this potentially lead to our disparities that we observe in terms of FPR and TPR gaps? So I'm a bit short on time. So I'll answer the question, and the answer is yes, it can. And we can apply recent methods in shortcut learning to try to remove the shortcut from our model. And the result is that we get a model that has better worse group accuracy. So we do again come with a trade-off of worse calibration and worse ERLC. Okay, better separation, so in terms of better TPR and FPR gaps, but worse calibration gaps. So again, we get models that are fairer, but models that worse in performance for all. So the summary is that in the shortcut learning setting, the trade-offs that we observe are very similar to the group fairness setting in terms of having a model that has better fairness, both binary and risk score fairness, and better your worst group accuracy, your group is defined as the actually cost of label, but we worsen overall performance for everyone, we worsen calibration for everyone. And so really this is trade-off between these metrics. Which one do you prefer? Though I think by targeting this specific mechanism in the shortcut learning, we may be able to achieve a better trade-off in that trade-off curve compared to the existing methods that we saw before in terms of blindly applying these algorithmic debiasing methods. So I'll finish with a few practical suggestions for implementing fairness in the clinical setting. The first is to evaluate comprehensively. To evaluate a wide range of metrics, threshold-free metrics, threshold metrics, calibration error, mean, white hat, and so on and so forth, as we see before. Second is to consider sources of bias in the data whenever possible. Consider label bias, sampling bias, distribution shifts, as well as how the model will moves downstream. And if possible, take steps to correct bias in the data generating process instead of blindly applying algorithmic intervention. Third, there is no golden solution to everything, right? There's many trade-offs that exist. Enforcing fairness will lead to generally worse performance and higher calibration error. And so really have to think about whether these gaps are justifiable for your case and whether these gaps are clinically justified, whether we should remove them at all. Finally, we see that having inductive biases about how disparate performance originates in terms of shortcuts may lead to targeted interventions in terms of trying to remove those specific biases. And this may lead to more favorable trade-offs on the trade-off curve, but again, the trade-offs still exist regardless. And to conclude, I'll say that I think algorithmic approaches are insufficient to ensure that the use of ML in healthcare is equitable. You really have to think about all those downstream and upstream pipelines, as well as data collection, integrating that all into your pipeline in order to ensure that you have a fair. Thank you for listening, and I'll take any questions.
Welcome back. It's our pleasure to welcome Judy Gichoya, Dr. Judy Gichoya, to speak on her work. She's an assistant professor at Emory University and also an interventional radiologist. I'm really looking forward to hearing about this work. It made a huge splash when it came out in, I guess, 2019 now. It was just before the pandemic, yeah?
preprint from a lot of work for the pandemic, and then finally, after many months of peer review last year. But I'll tell you that journey too.
Okay. I think it's especially interesting here at the Broad, just thinking about, not just about X-rays and potential confounders with race and things like that, but also how we think about genetics and diagnoses of genetic disease in the same context. So thank you for coming, and please go ahead.
So much for the invitation, and really great talk from Haoran. And he was actually in the initial group, not initial, he was in part of the group as one of the students working on the project. So knows a lot of pain points that we underwent through. So today I'm happy to speak about what I have evolved from that work to say it's this hiding in plain sight. And it's going to be more of like a bigger picture type of talk. And I love that the questions at the end said, okay, what do we think about this, shortcut learning? Because this is why I think this topic matters. And, I will, the way I'll just present it, I may present a point and say why it matters at that point. It won't necessarily be sort of like trying to do my 3 objectives, trying to talk about the cases and then the generalizability to figure out their utility. And finally, I'm going to pose a challenge, because this topic is not going to be solved by one person. It's going to require a lot of people working on it, and some areas to provide myself, feedback to me, but also to think about the research that's necessary to make AI safe for our patients. And so these are my disclosures. Mainly nothing that's going to be affecting this talk. These are just mainly grants and service work to many radiology societies. I already said what I'm going to be describing, which is talk about where AI has this superhuman ability to detect patterns that are not very obvious to the radiologist, and then to discuss how we have thought about possible mechanisms and explanations. This is a big area of research to make any radiology imaging useful, and to finally conclude with open research questions that need to be answered. Why imaging? I mean, for AI researchers, you may be excited because the imaging is probably what's available. And it's true, there are millions of studies performed every year. So at Emory, where I work, we do, I think, 1.2 million studies every year. So unfortunately, in the past, because people didn't have enough storage, we used to delete those images. So in the Emory data sets, maybe the best data that you can obtain is from around 2008. But if you have been unfortunate to go to the emergency room or to the hospital, you're most likely going to have some form of imaging done on you. And so this is, we don't really talk about how it's changing medicine, but it turns out that I can really see your hernia very well on your CT scan, instead of having to go and rest and have someone trying to palpate in your groin, trying to figure out where your hernia is. And so this is, subtle changes, especially in the era of telemedicine, where patients couldn't come to the hospital because of, sort of trying to decompress the hospitals. And so we will see imaging trends go up. And more so is that most of the work in terms of imaging data has been to make sure that there's reduced radiation. And so if we get to load those type of imaging, or more use of ultrasound, more use of MRI, we will, I think, exponentially see this increasing growth of imaging. And while people have said, well, it's the cost, I think that we may see even more targeted sort of scans. For example, taking an MRI takes forever, and this is an area of active research to see if deep learning can help accelerate that. But it may be that you just need to see how old my fracture is, and you just do one sequence of my foot, and you have the answer. And so, but at the same time, as we exponentially anticipate a big amount of imaging to be available, is that a picture is more, worth more than 1,000 words. And I'm going to quickly go through our study. And this was a collaborative work of many individuals, and just a fantastic way to work. Subsequently, this group still works together. And you can see everyone is listed alphabetically except me. And so we have our senior most author in the room just because of that. So it turns out that there's quite a lot of things in a name. And so the way we define race, and this was after many, many things, and I always start here, is that it's a legal and social construct. So it's how you would classify myself or how I would classify anyone in the room. And this is important because one of the big debates that came up after the release of this work is that our work was showing that race is a biologic, was supportive of this idea that race is a biologic concept. And I will not be going down that rabbit hole today, but it's a lot of work and a lot of things to explore and understand why that's important. And so essentially, we worked on many medical data sets. Some were described earlier. Emory is very unique because we do take care of a lot of Black patients. So usually our population is around 50-50 white and Black. Asian patients are rarely classified unless you're working with data sets from the West Coast. If you have a Stanford data set, you find people are more Asian populations. Now, if you are in Latinx, Hispanic, so this overlap of ethnicity and race, that's very difficult unless you are in, Arizona, maybe somewhere there. And this is because most of our EMRs, like where I work, you cannot have two races. You have to decide where you belong, or someone will decide for you. And so this is important, especially as we start to think about the groupings and the general ground truth that we rely on for models as we start to make group fairness, that you are really understanding how that data are collected, because they do affect how you downstream effect is. And so we worked on this data set. We really started off from a chest X-ray data set. This was going to be a short project. It was after George Floyd was murdered. Every journal wanted to publish a paper on, social injustice. And so it was, we were asked, hey, do you want to submit something? You had to submit an abstract. I said, I attended a datathon in Singapore the previous year, and I realized people are not using the imaging data sets a lot. And I said, look, this is going to be a hypothesis, which is sort of like what I think the so what is before when I'm, at the initial phase of a project. And I say, we're going to show that if you use the Mimic dataset, it's very relevant to here because, it's supported a lot by MIT and the Beth Israel Hospital. And I said, you will just require this dataset. We will show that you just need more diverse data. You need more Black patients. You will fix your bias. And we were going to repeat the work that was done, the preamble for the under-diagnosis work that was shown. And that was going to say, hey, if you see cardiomegaly and it performs poorly for white patients, if you bring it to the Emory data set where you have a bigger, better diverse data set, there will be no bias in cardiomegaly. We were very surprised because when we came to review the results, yes, the amplitude, the number of people who were affected in that group went down, but the patterns persisted. And so this is when we started to say, why was this model not responding to this diverse data set that we had shown it from Emory? And now, but that time we had gotten a feedback from the journal that I don't really think your abstract is a good fit. So got rejected that it wouldn't be part of the special issue. But now we were in this rabbit hole where one of the investigators came and said, look, it's because these models are able to identify the race of the patient. And then really that's how this work started. So we started off with chest X-rays, and then, we started hypothesizing, why is this, and I will show some of those results. They're really published. It's just a recap so that we're all starting off from the same page and move on to other modalities. And, there was never really anything novel, and there has never still been anything novel in terms of the, the deep learning approaches that we're using. But what we did at this point was to just test, more than one, architecture. But these findings always start if you show sort of like the training curve, but around the third epoch, you're already in the 90s percentile. So there wasn't anything that we were trying to fine tune. And another concept is we've shared this model a lot, and people usually are able to replicate the results without having to fine tune, which is your dream for when you start to think about deploying AI models in new settings, because we know that it's very difficult for you to just have good, even similar performance to what you had without fine tuning on some subset of the data in your target population. And so We found that the AUCs, to identify Black patients for chest X-rays, we were not using, there was no sort of retraining on a chest X-ray data set and then fine-tuning. This was just using image net weights as the initial point, was 0.96. Very surprising. We had around 6 radiologists on the group. Our performance was around 0.5, 0.55. It's very difficult to say, just look at a chest X-ray and say, oh, this belongs to a Black patient. Now, there are some things that can maybe help you guesstimate, which is, for example, if you see sort of braided hair, that mainly Black patients would have that type of hair. But that means that the X-ray was not acquired well, because usually you'd have to hold your hair away when you're getting your chest X-ray, and it shouldn't be in the field of view. And so there wasn't really any way for us to figure out why a human being would have a good ability of understanding distance. And we transferred it to other modalities. So you'll see probably the worst performing one is breast imaging, which is mammograms. The main point is that this is actually a task that AI models can perform very well. And so this is one of the biggest problems of doing any computer vision in radiology and, pretty much in medicine, is that we rely, there are many new things, ablation studies, occlusion maps, but some form of saliency map is what we rely on to tell you where the model is looking at. We looked at hundreds of these pictures. We never could figure out what's a pattern that tells you, well, maybe Black patients are, more muscular in our population, or there was just nothing. And this is a really good paper and presents some work an area of work that needs to be developed, which is understanding the utility of saliency maps. And people who've looked at it, even just by changing the order of these labels, you get different saliency features. And so this is an open area. I just put them there because you cannot publish a paper without including some form of visual thing where the model was looking, even if it's not very helpful. And so, later on when the paper was published, we had work that was done by Joseph Cohen, who was from Stanford, where he looked at this concept of explanation. And it's almost like you're stacking many, many similar images and trying to look at the latent encodings and trying to see what the differences are. And it gives you sort of like a GIF type of thing. You can see, well, maybe but all these are alphabetical, so Asian. And this is actually a pretty big deal if you're writing this type of work, that you no longer just start by saying white patients, you use them alphabetically. So if you say Asian, Black, and wherever order that you want. And most trends now are moving to capitalizing the minority groups when you're writing your paper. If you have someone who's very familiar in this space, that's super important for you to at least know that you have some knowledge there. And so this, was just showing, well, maybe it's the shoulders that are moving a lot, across different groups, but they still were not very helpful for us to figure out. It was good, and it was good to try something new, but this area of just looking at the images, understanding where the model has gone through. We've subsequently done some adversarial biasing work where you try to penalize the model for learning a protected attribute. But please don't forget what I said, that the group that you could be in may not be your choice. It may be that I looked at, for example, if you're from Turkey, you may not identify as Asian, white, or Black. And so, but people will look at you and decide based on your skin tone where they're going to classify you. And so, even if I say that the areas where the saliency maps are not helpful, we did block the areas where, we knew at least mathematically where the model was going to be looking at, and said, okay, is there other signal that that still contributes to this prediction? And you can see, in the regional, it was, high 0.9s. And then when we start to mask, the areas of focus, it drops, but again, it's still better than the radiologist. Aaron knows this a lot. He did a lot of this experiment that you'll see later. And you can see we started to say, hey, can we split the chest X-ray in terms of patches, and then pick one part or block it out to figure out what's this model looking at? And the patches still all have the same ability, But when we block out a patch, especially here, this is a very difficult area for just chest X-rays because the subxiphoid area has the stomach. So depending on whether the patient has fed or whatever is in the stomach content, you can have quite a lot of variation here. And also depending on whether the patient is sitting up, laying flat, that's an area that can change. That's our radiology explanation for this change, but we don't know if that's why we saw a drop when we look at just this sort of area here. And then we said, well, maybe let's look at the segments. Maybe it's the lungs only versus the the structural area. We do see lower performance for the lung, just when you look at just the lung tissues only, but we still have good performance for the non-lung segments, but this is still better than the radiology. So you can't really say, well, it's the non-lung segment that's contributing alone to this high performance. Then we started looking at blurring and adding noise. And this is moving to a segue of probably what I think is one of the biggest takeaway of our work. And here is just adding noise. And you can see when it's noisy, we see a drop. And when it's blurry, we see a bigger drop. But it's this ability when, if you say your dermatology AI algorithm is not working well, you show me 10 pictures, I can say, well, there seems to be a difference in skin tone. But the next few slides, what I'll show you is that this image degradation experiments, where it's very difficult for a radiologist to say, oh, this was a chest X-ray. It means that you even burden them because they cannot even tell you why is the model failing, because they cannot even perceive this image as the original, as an image that their eyes are trained to be familiar with. And so one of the experiments we've subsequently done is this CheckSpot data set. It's made from CheckSpot. CheckSpot is from Stanford. And this work was actually done to see in, back like in my home in Kenya, could you, well, maybe if my mother is sick, she may send me her chest X-ray via WhatsApp. But that X-ray is sort of like a picture of the X-ray. And so you would think that, well, if it's maybe the acquisition parameters or something on these images, the original image that's affecting this ability for the self-reported race detection, then when you take a picture using a Nokia phone, then you would lose that ability. So it's a picture of a picture. And we see, the CheckSpot is still actually pretty good if I compare it to the radiology. And so this was a big, actually decision maker, this and the digital hand radiograph, which is curated the same way, because it helped us move away from this theory that that it maybe have been the melanin that was interacting with the radiation and coming up with this, sort of affecting the prediction. And that had been a theory for a couple of weeks. We used to meet bi-weekly for quite a long time. And so this work again, so we start to see this downgrading of the pixels, right? This is a 4x4 chest X-ray. We still see, well, the performance is not in the 0.9, but we see this is 0.6. But this is barely perceptible. This is not a chest X-ray to any radiologist. And this work, which now nailed everything, and I like to explain it. I haven't spent a lot of time on this experiment because he did it, is to say, if you have TikTok and you can apply many filters in front of your image, is the same thing that we're trying to look, well, could you look at the fine features versus the coarse features? And if you tell me that this hypers filter here of 100 is a chest X-ray, I mean, everyone in this room agrees that you can barely understand that this is a chest X-ray, but we still see the performance of around 0.86. And so this ability, one that doesn't take long and persists on degraded images, is a big issue and still remains. I will show you some subsequent work, but it's really what made me pivot and start to say, maybe there are hidden signals. We don't know if they're confounders or shortcuts or whatever they are, but the models are able to detect them. And unless we understand this phenomenon, and I will show you subsequent examples from this, then we're not going to be able to mitigate any bias or make AI that is actually clinically useful. Just some sanity checks. These were many feedback and questions people are saying, well, maybe it's the equipment. We picked up just one X-rays. These are done from Emory. So this is important because the public data sets, the way they are curated and they're already released do not allow you to be able to do some of this type of work because, for example, you don't have the DICOM metadata, which can tell you this is the device that was used, or you're trying to do some of those experiments. A lot of people are trying to publish this. Actually, we're going to see some of these type of papers come up, and they're trying to manually try to change the physics. It's very difficult to do from JPEG. Please don't do that. That's not helpful. And so we were able to just look at test X-rays from our hospital. It's not the equipment. That was the big thing. This is something that we've never been able to expand on, and was also a good learning point for me. So every device that we use has to be calibrated. And by the way, in my unconscious bias, I was like, maybe the phantom is white, white in appearance, and maybe that's why it doesn't work well. This is the Emory phantom. There's quite a lot of technology that has gone to phantoms. Some of them used to use human bones in the past for calibration. Now with 3D printing, these have completely changed. So I invoked our physicists, and we went and scanned this using very specific protocols because, as we've learned from other areas, for example, the pulse oximeter, the temperature gauge, which we know varies a lot with skin tone, we do also have to look at the equipment and see why that matters. And what was surprising is that this is just one spectrum of one same patient. On one end, it believes this patient is Black, and on the other end, it believes this patient is white. Because, and we've never been able to really get large-scale phantom images, which is why we haven't been able to work on this further. But you'd expect sort of like a sigmoid curve that most predictions would be nonsensical, just sort of like where the radiologists live. And so what I'm showing this is that there's something around sort of image acquisition and thinking about those data sets that still remains unexplored. We did look at this experiment showing the pixel amounts. And this is important. This was just good for us. It wasn't because by the time you get a chest X-ray, you start off with raw signal. That's not usually available quite a lot to many people, actually even to us, because this is very. Should I answer that or should I go to a, okay. If we perform an unsupervised, Pamita, that's a good question. So this question is, if we perform an unsupervised algorithm, is it clustering on the X-ray data? Will it cluster primarily based on the race? We never really explored this further, but what happens in Emory is that you have, every time you get a chest X-ray, is that someone else had come up with another visualization, especially ICU radiographs, because you can have so many things on the patient. And remember, this is just one 2D view of the patient, and you're not sure, well, is this tube outside the patient or inside the patient? And so you get sort of visible light imaging. And so this is that every time I get a chest X-ray, it also takes a picture of my face, right? And the chest, it's not necessarily supposed to be for you to identify the patient on the face, but it's supposed to be saying, okay, maybe this patient has something, and their ET tube thing is on the patient, so that as a radiologist, you can quickly look and say, oh, okay, I know what that is, and it helps your interpretation. So what we have tried to do is, could you pick up those skin tone segments that you get on the visible light and cluster them to figure out, do you find new groupings? To do that is actually quite a lot of work because these images are acquired in at 3 a.m., right? If you've been in the ICU, 3 a.m. is pretty dark. And so you have to think about the processing very well. And if you work in the space of dermatology, then if you think about even the Fitzpatrick score, it's not sufficient in terms of telling you skin tone. So for example, I'm from East Africa. The East Africans have a lot of variation just on your face. You could have 3 or 4, different skin tone variations. And so I think clustering is a good area and could be even something that you do with sort of this pixel type of data, but we have not looked at that. Color averages. What he is just trying to say, before you're just looking at the at the image level. We did find that with just sort of like XGBoost, you can be able to tell the race of the patient. And so that it's not necessarily on the final processing that matters, but also at the pixel level. And so we looked at many anatomic variables. Does it change? Maybe it's only predicting well for people who are 60 because it's learning that they have disease. And the summary of this slide is that we could never figure out the why. And so, one of my friends said, have you tried shuffling the labels? Maybe this, and thankfully we shuffled the labels and we finally got what we would expect, which is sort of like this, 0.5 sort of randomness when you shuffle your test set. And so that was reassuring. And so essentially, after close to 18 months of work, we found that we have superhuman ability of the deep learning models to identify self-reported race across multiple modalities. And this performance was sustained on many external data sets. We could not figure out what was the confounder for this ability. And further investigation into the why was also unsuccessful. And again, I told you some of the bigger things that made me start to move to this hidden signal is, for example, looking at this high-pass filter applied to the chest X-ray and still having the same performance. And so other people, and this has shifted my work. Oh, okay. So this has shifted my work to thinking of to a little bit of not defensive, but like trying to validate other people's work. So we are seeing quite a lot of very strong opinions. One of them is this one. And this paper published in Nature Digital Medicine said the confounders mediate AI prediction of demographics on medical imaging. And this is probably the one paper I'm going to go into detail just because this is something, if you're reading in this space, you're going to see a lot come out. And this one uses echo. If any of you do ultrasound work, you know that it's very difficult. And this is because it's such operator dependent about how you acquire it. And they do a great job of trying to have different views. These are two Cedars Mount Sinai and Stanford data. You can see, that population are mainly male and mainly white. But what they do is say, could you tell us who's male and what's the race of the patient? And you see it's very good at identifying male versus female. Better than random, I think, to identify, Black, Asian, or white. And they also try to predict the age. And, the age, you can see the mean age was around the 60s, older population in Cedars Mount Sinai, and maybe a little younger patients in Stanford who get echocardiograms. These are just ultrasounds of the heart. And so they start to do some different experiments. And so in this data set, which is saying it's unadjusted, you can see that the population of males is higher. So this is one thing that a lot of people are doing. I would urge caution with this. You cannot group minority groups as rest. They say you don't have enough data, and you cannot keep saying white versus rest, Black versus rest. No one is ever going to be able to replicate those studies. And that's one of the big sort of cautions as we see here. And they do something about this biasing the data set, like this varying the training data set size. And they bring in what they call the bias factor. And essentially, if you have like 0.8, for example, this would be a bias factor of 0.8. What they show is that if you have a bias of 0.8, in this case, what they're saying is you have white males 80% and your non-white male at 20%. And your white female is 20%. So it's almost like a cross, right? So you have your white male 80, but that matches the white female, right? So it's a cross. And then they start to say, look, that fixes this, you lose your predictive ability for the race of the patient. This is, I think, one of a troublesome experiment because what's happening is that you already have a model that's very good at identifying whether the patient is male or female. So if you split your data set this way, then your data set is already, your bias does not say that, well, in the future data sets, you just need 20% males and Black males, 20% white males, and that gets rid of your sort of this ability, like penalizes your model for, detecting Black patients or white patients or white Asian patients. But we're seeing a lot of these sort of experiments trying to say, what's the right data set composition that allow us to say, this ability that if you it's because your data set wasn't composed very well, that's why you have this ability to detect it. I spent some time reading this and replicating it. So, for example, we ran the same and showed that it doesn't matter on your original distribution, that you still have the same performance, except one at bias one. But you can imagine if you have bias one, then you completely just have white males and white females, right? So you don't have this other group there. So this paper concludes, race prediction comes from shortcutting through known confounders. In this case, they were changing sex and age. But what's I think we're going to see a lot of these type of papers coming up, coming down the stream. And apart from this one, there have been other small papers that have said, not small papers, just papers that have said, we think this is this prediction, but no one has come up with a why. Even for our own research team, we haven't come up with why this occurs. And also, which is why I'm trying to change to the next portion of my talk, is why this matters. And so this is work that we did earlier, still in the pandemic. And we just used chest X-rays to say, could you predict ICD codes? ICD codes are used to document diseases. So an absent ICD codes, for example, if my record is saying I don't have congestive heart failure, then that's actually a disparity. And so, well, very, very simple. Again, this is 15,000 patients, trained to predict 6 labels. I'm going to show you what those are. This is a ResNet 34. Nothing novel in terms of the training. And we start to see, okay, well, this is the predictions of diabetes, obesity, arrhythmias. You can look at the obesity, you start to see where the model is focusing on both subcutaneous tissues, and around just the whole body. If you're looking at arrhythmias, you see more activity around the heart. And this data set, we actually included something interesting, which is the social deprivation index. And the SDI is important if you're doing sort of disparities work, because it's like it combines demographic data of poverty. It tells you high school dropout, renting, lack of car ownership, unemployment, and maps this onto a single zip level code ranking. And so if you have a high SDI, you live in a poor area, and low SDI, more affluent area. And we'll link this to the chest X-ray prediction model. And what we find is that you can tell the SDI of the patient just from the chest X-ray. And you can also, with AUCs between 0.76 to 0.9, you can predict those 6 conditions. And so this brings it home where you say, okay, this was a patient, Spanish speaking. And why that's important is if you've had to get history from a patient who doesn't speak your primary language, it's really difficult, because you have this this computer translator that's terrible, and you have so much work to do. So you just focus on what you need. You're not really, we'll just have to be honest, that we're never comprehensive in terms of that type of data set curation. And so, this did not have congestive heart failure, but was labeled as congestive heart failure. And when we went through the chart, we found that this is a patient who lived in a high SDI area, had a history of diabetes, non-compliant with medication, and a few years prior had an echo ordered, but was never able to get it. And so I can tell that you're Black, you live in a poor area, and these are your ICD codes. And then I can tell you that these are your future expenses. When we look at this work was done from the Stanford training, again, nothing big. This was 20,000 patients, being trained to predict future healthcare expenses. Now, I will have to say, for example, they train 4 models. The T model looks at age, sex, and zip code. If I say those words, you do know that they can actually tell you a lot. They have so many proxies. And so, but they also train an image model alone, and that's the X, which is this one, which this T model is the one that most likely is just being fooled by the variables that you're selecting. And then they start to, fuse this other, the multimodal fusion, or use the non-clinical, sort of like the text data and the imaging data to get this TX1 and TX2. But they actually have good performance of their model. This is, I can tell you some of the patients who are going to spend more money, but you can see the 1 year expense, 2 year, 3 year, and 5 year expense. And they give some examples. And, these two, just from a radiologist, the saliency maps are not very helpful here, but this is a chest spot. So if you have a chest spot, you either have cancer or are requiring quite a lot of contact with the healthcare system. So I would expect your cost to be high. And this is a normal X-ray, so I'd expect the cost to be low. They showed the examples that didn't work very well. This to me was just something multifocal, but looking at the shoulders, I can tell that this is a young patient. So maybe they just had pneumonia. And so this was predicted to be very high, but turned out to be low. And this case was predicted to be low, but turned out to be high expensive. But I can see that this aorta has some calcium, is ectatic, so starting to become dilated. And if I look at the shoulders here, they look old. And so for me, this is an older patient who may not have an acute illness, but you can see that the model starts to get this strong. And so different type of work showing biologic age. This is not unusual. You go to a patient room and they say they're 80 and you're like, what? You look 60, So visually, we know that this is something that happens. But on imaging, it turns out it's the same. You look at the aorta and it does not have any calcium. The patient is 80. I mean, that's a patient who's aging just different. And so this group looked at chronologic versus biologic age as a marker for cardiac risk prediction. Again, nothing new in terms of the deep learning approach. This is just still a simple CNN, looked at clinical trial data set, because in this type of work, you need a long-term follow-up, and I started to predict this chest X-ray age, and then start to bin the buckets that show the differences between the chest X-ray versus your chronologic age, which is what you would say your date of birth was. And these are some of examples on the right side here are patients who chest X-ray age is less than the chronologic age. So you're aging slower, you're young. Your biologic age is young more than your chronologic age. All these patients who are alive at the end of their follow-up. And these patients where your chronologic age is, your chest X-ray age is older, so you're aging you have a higher biologic age, who are dead by the time of the end of follow-up. So essentially what I'm saying is Judy's Black, from chest X-ray, Judy's Black, female, 60 years, biologic age, maybe 78 years. I live in a poor area with a high social deprivation index. And these are my ICD codes. I have congestive heart failure, COPD. And my next, my health expenses in the next, 1 year or 3 years is 15,000 USD, just from chest X-ray. But we cannot understand why these models are able to tell these signals, but we see performance. We don't know why this matters. And so the first one I'll say is that now we're starting to see startups say, I'm going to tell you how you should underwrite for the patient. And we don't really know how this is working, but insurance companies can buy your chest X-ray. In fact, they may get it as part of providing you insurance. And if you've had to get life insurance or disability insurance, then they have to send a nurse to your house, you wait, all this paperwork. But if you could try and get a good estimate from this chest X-ray, I'm not saying that it's accurate, but if I could convince you that I could provide it to you, I don't see why people are not going to embrace this type of technology. We discussed a little bit about shortcut learning. And this is important to understand. We've known that location matters a lot for chest X-rays. This has been repeated many, many times. This is a great paper that just looked at why all the COVID models couldn't work. They learn from where the patient is. And till we understand we don't really know what, like the so what, when it comes to understanding the significance of the hidden signals in terms of understanding the role of confounders. We've seen a lot of amazing work, actually. It's not necessarily bad. This is, Nancy is a patient who's passed away, changed a lot of how breast litigation works. And this is because she had dense breasts and breast cancer was missed and was devastated, and quite a lot of change. But we've seen a lot of AI algorithms try to predict the risk of breast cancer just from images alone, with a good, actually, performance of the 5-year risk of breast cancer. Now, I do draw some circles here. It really doesn't tell you where the AI is looking at. It just tells you this is the risk of breast cancer. And I think this is good if you look at the current state, which is that, so this is the Mirai model, actually from Harvard, and we did validate this. And if you look at the existing clinical models, they're not very good. And for Black patients, these AI models tend to perform well. But the question here is this model relying on this confounder of understanding Judy is Black, Judy lives in these places to get this signal? And it's okay if we can harness that signal. But remember, the population is changing. There are many people now who identify as mixed race. And so how will this model work for these patients? And we've seen the same type of work by Emma Pearson looking at osteoarthritis, showing that AI models can narrow the disparities for pain. And when you look at the data set that they used for predicting this finding, we see that it's pretty easy to tell what the risk of the patient is. And so, well, I don't want to be a Debbie Downer, but I started off by saying we have amazing, growing exponential amounts of imaging. And this provide opportunistic, screening opportunities for screening, even when you're not really performing that study for that purpose. We're seeing a lot of this come into the cardiac care space. And these hidden signals don't really require human curation. You may have some data, but I'm not going and trying to draw the abnormality. And so they provide an increasing opportunity for you to study this well, but we still don't understand, first of all, we have these patterns, differences in who gets imaging. For example, Black, Hispanic, and non-white patients are less likely to go undergo diagnostic imaging in the emergency room. And so if your hidden signal is picking up on something like this, then you're going to just perpetuate bias. And you may not be intentional, but this may be happening in the background. And similarly, when we've seen this type of publications, for example, a minority serving hospital, and this type of data, especially as was demonstrated prior, that it's not just the imaging, but also the notes, and we're starting to feed this into the model. I think this hidden ability is not just a bias issue, but also understanding the true performance and models that are learned. So it would not be a talk if I don't include something about the fusion model, right? And so we see this is also coming to medical imaging. This is a data set curated from the UK Biobank. Visually, to me, it looks, I could not tell which one is the synthetic data set versus the one that is not synthetic. And but in our work, actually a follow-up work that's not been published yet, what we've seen is that the synthetic data sets still propagate some of these demographic signals as you move downstream. And so as we are very excited to see some trends, for example, a lot of, I think Google is working on a lot of embeddings, because people are trying to overcome this challenge that we don't have enough data set. This work, I think it's interesting, said you only needed 45 chest X-ray radiographs to train a COVID model prediction. This was actually for tuberculosis, but they had done something similar for COVID, and you had a value of 0.95. But if you're trying to say your original data set has hidden signals, your synthetic data set has some signals, but you don't have a way to audit it, you still don't know what the embedding space will look like in terms of propagating the same signal. But also remember, a lot of people have said, hey, it may be that we can create race neutral or gender neutral data set, but you use the same approaches, but we have to be understanding of what these hidden signals mean. So what do I think are the areas of research? I think that we do need to curate and inform how to develop better data sets. They don't need to be perfect, but we have to understand how they are acquired, and also move away from these studies that are just trying to say, this balancing is sufficient. I do think it's not going, this is being recorded. So I will say that I don't think that's going to be the solution. And so I think another area is explainability, where as people who work in medical imaging space, it's very, very difficult to understand what the models are looking at. I think this is a really ripe area in a way that is understandable to the radiologists. We're seeing something different. I don't know if any of you have seen this Röntgen paper. And here, what it does, you just give it a prompt, and then it tries to generate an image for you matching that prompt. So for example, if you say, show me a patient with bilateral pleural effusion, it can show that to you. And I did try it actually. And I said, show me a patient with a chest tube, pneumothorax with chest tube and one without chest tube. The chest tube, I mean, is kind of cut out. So like from a medical imaging perspective, that's weird, but at least it was there. But this images did not have any pneumothorax, but it were labeled as having pneumothorax. And so as we start to see this type of ways of generating new data or this type of reverse prompting and image generation makes sense to me as a radiologist. But I think this is still like a big, big area for research in terms of explainability. The next one is to rethink how these hidden signals affect our validation. We know already that we don't do a lot of validation. We know that performance drops, using the out of distribution data, but I think we need, and our group is starting to do this, where we're starting to run silent clinical trials just to see what are these models learning. But this is a really inefficient way of doing AI research because there's such human component in decision making that's very difficult to quantify from notes or anything else. So I don't know what's going to happen there. So maybe in future I can come and tell you what we find. And more importantly is that this area of bias is going to be regulated. I think this is one of the opinion papers that has generated a lot of opinion. And some of the big summaries are that people are going to be penalized if your model doesn't work well for a specific group. Remember what was demonstrated earlier, you're always at an intersection. For example, you could lose insurance and you could be Black on Medicaid, but when you get insurance, you're not Black on Medicaid. And if your model, we don't really understand what happens, how our intersection changes as we move on with our lives and how this AI system adapt to that. So I think that in our work, we have to inform policy, else we'll have laws. People who have reacted to this are just saying, well, you're going to stifle innovation. But I think that we'll use different lessons from understanding innovation and also really grounding the work that needs to be done is really a call to action to everyone in this room, because this work will be super important to make sure that AI can be used. As always, I always end with this slide here from, actually got it from Maziv, but work with Irene. And this is just that this AI space is really difficult to work on. When from your point of problem selection, I have examples of those. I'll give you actually an example. One of the reactions and feedback from our work was, hey, maybe you should look at one of the anti-abortion medicine and how it affects the breast changes, because would that be the explanation for this for one of our data sets? And by then we didn't have Roe and Wade versus Wade overturn. We live in the south part of the country, and now you can imagine you'd have, if you just always jump on projects, you would have this data set with like really critical information, even if you've anonymized it, studying something that's not going to change much of our outcome, but could have detrimental consequences if publicly released. And so from the problem selection to defining your outcome, deployment, and post-deployment considerations, I think we see quite a lot of examples here where we've seen just the classic clinical models like sepsis model from EPIC fail. And so I think we're going to see interesting examples, and I can postulate that some of those will be from these hidden signals in this step 4 and 5. Most important thing, if you're ever interested in this type of work, we're always looking for postdocs. Atlanta is hot. I had to really repack my things before coming here. These are some of our lab mates. And in August, we're going to host a datathon that is going to look at this concept of data set and bias. And I hope that I'll get to see some of you there. Thank you. Thank you so much again for the invitation. I hope this was interesting and helpful or inspiring to keep working in this space.